Hello, and as I finished that last video, I realized I actually had some extra time, so I'm sorry. We're just going to pick it back up where we go and just keep continuing on with our videos. So, welcome back. So, last video we left off at problem 5, part B, selecting probability between these years. So we set it up, and once we set it up and solve, I'm going to go relatively quickly though. You get negative 0.88 and negative 0.23. Remember, these are going to be our z values, and when we have our z values, we're going to go to table B in the back, and table B is going to tell us that value and less than. And when we look these values up, this is what we're going to get. These are our probabilities, so in this 0.4090, and then we're going to subtract them from each other. Remember, you're always going to subtract the larger value from the smaller value. If you don't, you're going to come up with a negative number. If you come up with a negative number, probabilities can't be negative. That'd be a clear sign that something went wrong. So always keep that in mind. Remember, probabilities have to be a positive value. It has to be between 0 and 1. You can never go to a craps table and have a negative 10% chance of winning. There's always a probability of winning. It might be very small, but it's not negative. So number 6 and number 7 here, moving on, we're going to be talking about our chapter 9, which is with our null hypothesis statements, and this is where things start getting a little bit more in depth, and it's important to understand the 5 steps that we're going to be doing here. So when we say write out a 5-step process, automatically you should be thinking that we're going to be doing like a hypothesis test here. So we're going to, on the side, write the information we know. So here we have n equals 64. We have our standard deviation equaling 0.8. One thing always to keep in mind, if you collect information from a group of people, participants, individuals, however you want to name it, and then you're given a sample average, anytime you see sample average from a group of people, that's always going to be your x-bar. So x-bar is equal to 6.4. As we read on, we're looking to see if we can increase how much sleep we can have with this new drug, and we want this new drug to be better than what is considered probably the standard quo or the norm right now at 5 hours. So we know our mu is going to equal 5. One thing to always keep in consideration that I see people, a lot of people are reading this problem, and they see all these numbers and they're trying to figure out what is what. Look at what we're doing right off to the side. N equals 64 standard deviation. Anytime you see a sample average, that's going to be your x-bar. Then once you do that, take a step back and look at the problem. What are you trying to do here? You're a researcher. Try to put yourself here. You're a researcher. You have this new drug. You're trying to see if this drug is better than what's currently available for these elderly people who have sleep apnea. Or sleep insomnia, I'm sorry. And if they have insomnia, that means they're not getting much sleep. So we want to get them more sleep, right? We want to increase the amount of sleep they're getting. Increase hours. If you see increase, we're automatically going to be thinking it's greater than. It's going to be greater than. So how are we going to increase it? We're going to increase it above 5. When you start thinking about the problem this way and how you're setting up, you're the researcher, the steps start kind of flowing. All right, so the current standard right now, our null hypothesis, is going to state that mu is equal to 5. We, as the researcher with all alternative hypotheses, are going to state our mu is going to be greater than 5. We're going to increase how many hours of sleep they're having. Now we're going to set up our z-test. And remember, the z-test is very similar to a z-score, a little bit different, but we're doing kind of the same stuff, where it's going to be our x-bar minus our mu hypothesis over the standard error of x. Standard error of x is the standard deviation over the square root of n. So when we put this all together, our x-bar is 6.4 minus 5 all over 0.8 over the square root of 64. Simplifying this down a little bit, step by step, because that's how I like to do it, we're going to get a value of 14. Now remember, what is 14? Well, 14 is your z-test. That's what we're solving for. This is equal to z-test, so this is equal to z. What do we know about z? Z is just a fancy way of saying how many standard deviations from the mean you are. How many standard deviations away this group of people that take this drug is from what's considered the normal, the normal population here that take a different drug. They're 14 standard deviations, so it's really far away. Our book doesn't go to 14 standard deviations. If it did, you would see a very small number, but anything really after 2.5, 2 standard deviations, you're going to pretty much find significance. So our z is 14. We go to our largest area in the back, that's going to be 3.49, right? And we're going to see a p-value, or we're going to find that to be 0.9998, right? But once again, table B is going to tell us this value, and this is table B is that value and everything to the left. So everything to the left. But we're looking at greater than. So we want to find everything that's going to be greater than this. So we take 1 minus 0.9998 equals 0.0002. This is now our p-value. So we have our z-score, our z-test is equal to 14. Our p-value is equal to 0.0002. You can also write that 2 times 10 to the negative fourth, right? 1, 2, 3, 4. Yep. Either one is fine. Now we're going to look at the significance level. I'm going to just put sig level. So the sig level is found on page 204. It tells you at the p-value what is the significance of that p-value. And you'll look and you'll see that this is highly statistically significant, or it's statistically highly significant, I think is how they say it. Highly statistically significant. It is less than 0.01. That is the key. There's those 4 different tiers. Either it's greater than 10%, it's between 5 and 10, it's between 1 and 5, or it's less than 1. And each one of those gives you a tier. So this is less than 1%, our p-value, so we'd say highly statistically significant, and then our p-value, if our p-value is less than alpha, we're going to reject the null hypothesis. Our p-value is 0.0002. Our alpha here, well, if we have 95% confidence, our alpha is going to be 0.05, because confidence in alpha will always sum to 1. So if our alpha is 0.05, and we put in this inequality here, does this make this inequality true? It does. Therefore, we are going to reject the null hypothesis. And that's how we set up number 6. Moving on to number 7. Try to do number 7 relatively quickly anytime I have. Once again, write off the stuff that you see on the side. Put yourself in the researcher's shoes. Here you have a breast screening test where you want to reduce how many false positives there are. False positive is when you get a test that says you are positive, like a birth control or like a pregnancy test. If you take a pregnancy test, it says you're pregnant, but you're really not. That'd be a false positive. We don't want to give false positive. You don't want to tell someone that they are pregnant or that they have HIV or that they have cancer when they really don't. So we want to reduce how many false positives there are. So when we go through here, right now, the current false positive rate for a mammography is 12%. So since it's the current or status quo, we know that's our mu. Mu is going to be 0.12. We know our standard deviation is going to be 3%. So then we take our new device that's going to test for breast cancer for mammography, and we have a simple random sample. Remember SRS, simple random sample, 245 patients, so that's our N. And that their average result, right, their average, the sample average rate of false positives is 6.5%. So if that's the sample average, that's your X bar, 0.065. Put these in decimal forms. So now we're going to write out our 5-step process using alpha at 0.05. When we write this out, so our mu is going to be equal to 12. We as the researcher want to reject mu, and we want a better machine that's going to give better results, so our mu is going to be less than 12. We put in now our z-test formula, which is x bar minus mu, which is standard error of x, so 0.065 minus 0.12 all over 0.03 over the square root of 254. when you break this out, so again, I'm going to break it out. That's how I do. Remember, you're taking a little number minus, a little number minus a big number, so you're going to get a negative value. And that's what we want. We want negatives when we're less than, because we want it to be less than what's currently going on. So that's a good sign. So you can get negative 0.055 all over 0.0019, which is then going to equal negative 28.94. Now remember, what does this equal? This equals z. What is z? Z is just a fancy way of saying how many standard deviations away from the mean you are, or how different this group is from the average group that normally uses the other mammography screening. Negative 28 is a super high number. It's super far away. And if we were to table B in the back, right, we have a z value. If we go to table B in the back, table Beyonce, it tells us everything from that value into the left. And since we're looking for less than, if you take your left hand, it makes an L. And if you didn't know that, now you do. And if you close it just a little bit, right over it, right, you're going to make the less than symbol. Left, less than. Table B is table Beyonce. Everything is to the left. So we're already finding that value. So we go to the smallest value there, which is already going to be 0.0002. That is going to be our p-value. Truly, it's much smaller than that, but for the purposes of us, we know that's a very small p-value. So we're going to write off to the side now. Our next one, our z-test, is equal to negative 28.94. Our p-value, I should write that the right way, hold on. Our p-value is equal to 0.0002. Our significance level, once again, remember that's found on page 204. Since it's super small, we're going to say it's highly statistically significant. And since our p-value is less than alpha, right? If p-value is less than alpha, we reject. Same thing here. P-value 0.0002 is less than 0.05. Therefore, we're going to reject. R-E-G-E-C-T. No, what happened there? Reject the null hypothesis. And now I'll do it for number 7. Number 8 and number 9 are confidence intervals. I'm not going to be able to get through that in the next minute, so I will pick that up on the next video. I will see you there.